Okay, so last time we started talking about random vectors or multiple random variables. So basically we think of a bunch of random variables, x1, x2 till xn, and we can think of them as like components in a random vector in the n-dimensional space. And a random vector basically is characterized by its CDF, which is the joint CDF of all of its components, the random variables x1 till xn. And so this joint CDF is basically this probability here. So the probability that big x1, the first random variable, is less than or equal to small x1, second random variable is less than or equal to small x2, up to the nth random variable being smaller than or equal to small xn, okay, where those small x's are, of course, real numbers. And this probability, again, I can write it like this is like explicit to show the components of your random vector, or like in a compact form, this can be written as f of x, and it will be understood from the context that this small x here is not just a random variable, but actually it is those n random variables. Now, the CDF has properties, and so for example, if you take the limit, okay, so again, if we write it as a probability x1 less than x1, and then some guy here, xk less than or equal to xk, okay, and then if we take the limit as xk goes to minus infinity. So for every k, this will be true for every k. So if you ask yourself, what is the probability that one of those guys is less than or equal to minus infinity? So this probability is 0. Now, if you take the limit as all those guys going to plus infinity, so what is the probability that x1 is less than or equal to plus infinity, and x2 is less than or equal to plus infinity, and x3 is less than or equal to plus infinity, and so forth? Then this probability will be 1. The function is right continuous in each of its variables. And then last time we stopped at the rectangle inequality, which is basically this condition here. And this condition like may look mysterious, so I said that, you know, basically let's try to investigate it when we just have 2 random variables. Okay, so for the case when big N is equal to 2, basically this rectangle inequality will be this probability here. Okay, or let's say that it will be, let's not say probability, let's say that it will be this expression here. Okay. And so what is this expression? So basically we have 2 random variables. So let's imagine them. So this is x1, okay, and this is x2. And then we choose a1, basically a1, a2 is less than or equal to b1, b2. And this inequality is to be understood element-wise or component-wise. And so basically this is A1, it's here. This is B1, and this is A2, and this is B2. Okay, so let's see actually what is the meaning of those terms here and how do they combine. What's the meaning of basically this particular combination of them? So let's start with this guy, fx1, x2, b1, b2. From definition, this is the joint CDF. So this is the probability that x1 is less than or equal to b1, comma x2 less than or equal to b2. So this is this probability. So basically, this is the probability that the ordered pair x1, x2 is in what part here in this 2-dimensional plane. So we are talking here that x1 is less than or equal to b1 and x2 is less than or equal to b2. So we are talking about basically, you know, the probability that of this event here, the event that, you know, x1 again is less than or equal to b1 and x2 is less than or equal to b2. So it will be basically this probability. But from this probability, we do something. We subtract these 2 terms. And each one of them is itself a probability. Okay, so let's basically write the coordinates of the points. So this point here is b1, b2, and this point here is a1, a2, and this point here is a1, b2, and this point here is basically is B1A2, right? And so what does it mean that we subtract this one here? Okay, so again, this is a joint CDF. It has a very specific meaning. This is the probability that the first random variable is less than or equal to B1, and the second random variable is less than or equal to A2. So we are talking about the second random variable being less than A2. So this is A2 here. So this is A2. So we want the second random variable to be below this line, okay? And at the same time, we want x1 to be below b1. So we are basically talking about it. So this probability is basically this part here, that x2 is less than a2, and x1 is less than or equal to b1. Okay, so this is this term here. And so what happens if you take this guy here with the plus sign and this guy here with the minus sign? So now we have the probability, so these two guys together, so the last two terms here, will give you the probability, here again, here is x2, here is x1. Now we are talking about the probability that x1 and x2 are basically in this guy here, so in this region, okay, and and this is a1, this is a2, and so on, okay. Again, because we started with the probability that x1 is less than b1, x2 is less than b2, and then we subtracted basically this, this probability here that x1 is less than or equal to b1 and x2 is less than or equal to a1. Then there is another subtraction here, and this one is the probability that x1 is less than or equal to a1 and x2 is less than or equal to b2. Okay, so here we have x1, so this is a1, x1 is basically below this. Okay, it's below this. Okay, so so if we draw this will be this area. So here is x1 less than or equal to a1 and x2 less than or equal to b2. It will be basically this area. So we subtract this again. So when you subtract this, what will happen? So when you subtract this, basically what you get is the probability of this box here, right? The probability of this box, because you subtracted this. But also there is something here that basically this part here, this part is subtracted twice. It's subtracted in this term and subtracted in that term. And so this is like subtracted twice. So this part subtracted twice. And this part is basically the region that x1 is less than or equal to a1 and x2 is less than or equal to a2. So if you add this term, if you add it, okay, then you end up with the box. Okay, so this long story is just the probability that the random variables x1 and x2 are specifically in this box here. Okay, so they are basically what this expression here, which again may look like sort of mysterious, but it is nothing but this probability that x1 is living between a1 and b1 and x2 is living between a2 and b2. And since it is a probability, then it makes sense, that basically that this thing is greater than or equal to 0. So this rectangle inequality is sort of like the generalization of the monotonicity of the CDF. In one dimension, the CDF is non-decreasing. It may remain constant, it may increase, but it never decreases. So this is something, similar, but for, multiple random variables or random vectors. Okay. Now, what is basically the CDF of one of those random variables? So we have a bunch of random variables right now. So we have, again, big X now is components, and each one of those guys is a random variable. And what if we are interested in the marginal CDF? So by marginal CDF, I mean the CDF of one of those component random variables. Let's say that you are interested in the marginal CDF of X1. So if you know the joint CDF, if it's known, if it's given, so how do you obtain, the CDF of one of those guys? Okay, so the idea is, if you know the joint CDF and you are interested in the CDF of xk, which is one of them, and this is true for every k from 1 to big N, then what you can do is that you can take the limit of the x's, small x's, except xk, and you put them equal to infinity. So why is this the case? Again, it may look mysterious, but if you write the joint CDF as a probability, this is big x1 less than or equal to small x1, and then you have xk minus 1 less than or equal to xk minus 1, and then xk less than or equal to xk, and then xk plus 1 less than or equal to xk plus 1, and so forth. So this is the joint CDF by definition. Now, if you want, basically, so from here, what is desired or required, okay, is basically the probability that xk is less than or equal to xk, which is the CDF of one of the guys. Okay, so we call this one marginal CDF, which means that it is the CDF of one of the components of, of the random vector. So what is this? So we are interested in this probability. So, you may think that this can be obtained from here if we go to those parameters and set them to plus infinity. So if you put this guy as plus infinity, and this guy as plus infinity, and this guy as plus infinity, because if we do this, we are saying, what is the probability that xk is less than or equal to small xk, and x1 is less than or equal to plus infinity, and x2 is less than or equal to plus infinity, and xk minus 1 is less than or equal to plus infinity, and xk plus 1 is less than or equal to plus infinity, and so forth. Okay, so basically the event that x1 is less than or equal to plus infinity is a sure event, right? It is, x1 is less than or equal to plus infinity, x2 is less than or equal to plus infinity. So if you take the limit of every other guy except small xk going to plus infinity, then what you end up with is basically the probability that xk, big xk, is less than or equal to small xk. And so that's the CDF of basically the random variable big xk. Okay, so to marginalize, which means that if you want to obtain the CDF of one particular random variable inside your random vector, what you do in the formula for the CDF is that you take the limit of all arguments except xk basically to plus infinity. And in this, this case, you will obtain the CDF of one of the guys. You can generalize this idea if you are interested in the joint CDF of not just one guy, but a subset of those guys. Okay, so suppose that you are interested actually in obtaining the CDF of xi1, xi2, xim. So those are basically a selection of random variables from the random vector. So suppose that basically your indices. So we have n random variables. They are indexed by 1, 2, 3 up to n. Suppose that you can write this set as two disjoint sets, I1 till im, union j1 till jn minus 1, jn minus m, sorry. And so basically, if you can write those indices as the union of those two disjoint sets, and suppose that you are interested in basically the CDF of those guys. Okay, so the same idea is go to the other guys, so basically the remaining guys that you are not interested in for some reason right now, then take the limit as they go to plus infinity. And if you do so, then you are left with the CDF of the required guys, which are, big xi1, big xi2, big xim, and so forth. Okay, so this is an example that suppose that you are interested in the joint CDF of x1, x4, and x5. Just these three guys, and you have the joint CDF of the 5 random variables x1, x2, x3, x4, x5. Okay, so you are interested in x1 and x4 and x5. So the remaining guys are x2 and x3, x2 and x3. And so what you do is that you start with the joint CDF. And from the the joint CDF, you take the limit as small x2 and small x3 go to plus infinity. Okay, so so this this will not allow you just to obtain the CDF of one of the random variables, but you can obtain any, basically the joint CDF of any selection of those random variables by doing this trick of taking the limit of the others, going to plus infinity. Now, what about like the other basically question of obtaining the joint CDF from the margin? So if you know the CDF of x1 and the CDF of x2 and the CDF of x3 and so forth, can you construct the joint CDF? And the answer is generally that this is impossible to do. Okay, so what I'm talking here is that if you know the joint CDF of the random variables inside the random vector, then by using this limit, you can obtain the CDF of one of them, or you can get the CDF of any selection from basically those random variables. Now, if you know the CDF of each, so if you know the CDF of x1 and the CDF of x2 and the CDF of x3, can you use this information to basically construct the joint CDF? And the general answer is this is impossible. So the marginal CDFs, yeah. So basically, this is the idea that there is one situation in which this is feasible. Okay. So generally, this is not possible unless we have independence. So this will be my next topic. So if the random variables, again, if you know each one of those guys, okay, can you say something about this thing? Okay, and again, this is generally speaking infeasible. Those guys do not carry enough information to construct the joint CDF, except when you have independence. And so what is independence? So for random variables, we have independence. Okay, and so we'll take it like sort of a matter, this is the way of defining independence. We say that random variables x1, x2 till xn are independent if and only if. So basically, this is like a condition, that if you find condition satisfied, then you know that the random variables are independent, and if the random variables are independent, that you know that this condition must be satisfied. If we can write the CDF, the joint CDF of those random variables as a product of the CDF of each one of those random variables, if this is possible, then the random variables are said to be independent. Okay, so again, if you just take two random variables, x1 and x2, if they are independent, then in that case, the joint CDF of the two guys, and again, don't forget what this means. This is the probability that the first random variable is less than or equal to small x1, and the second random variable is less than or equal to small x2. Then you can take this and write it as basically the first CDF, marginal CDF, and the second marginal CDF. You can write it as this product, which of course is as a meaning. This is the probability that x1 is less than or equal to small x1, okay, x2. So so basically, this is the definition of independence. And so you can see from the definition that if your random variables are independent and you know the marginal CDFs, you know the CDF of each one of those guys, then if you want to know the joint CDF, you simply take those individual CDFs and you multiply them. And by multiplying them, you simply get the joint CDF. Okay. Otherwise, again, if you don't have this independence assumption, then basically you cannot basically obtain the joint CDF from the marginal CDFs. Okay. Now, what is the meaning of independence? What is the meaning of the independence of random variables? Again, ignoring pathological situations and so on. In the overwhelming bunch of situations, independence of random variables means that if you know one of the random variables, you have no information whatsoever regarding the other. Okay, so the intuitive meaning, again, it will work for you in the overwhelming majority of practical applications. The meaning of independence: if two random variables are dependent, it means that if you know something about one of them, then you can say something about the other. But if they are independent, then observing one of them, measuring one of them, tells you nothing whatsoever regarding the other random variable. Okay. Now, in many of the theorems of probability and statistics, we don't just have independence. Independence makes life, very easy relative, to the case in which the random variables depend on one another. But sometimes we actually basically push things further and assume that the random variables, they are identically distributed, so they have the same marginal distribution, the same marginal CDF. Okay, so sometimes it's not just that, that basically we can write the joint CDF as the product of the marginals, but actually the marginal CDF of each of the random variables is exactly the same. And so in that case, we talk about random variables that are IID, independent and identically distributed. Okay, so for example, if you have that x1, or let's just say x and y, or x1, x2, okay, not a problem. x1 and x2 are IID, normal or Gaussian, so this is Gaussian distribution, mu and sigma squared. Okay, so it means that each one of those guys is a Gaussian, is a Gaussian random variable, and so basically, the Gaussian random variable is characterized by its mean, first moment, and its variance. But if they are IID, so they are, they are independent, and also they are identically distributed, which means that the PDF is the same. So in that case, you can, as we'll see later, that you can write down, the joint CDF as the product, and it's basically the same parameters for every one of those guys. This is like sort of the easiest scenario in probability and statistics, the IID case, and it's most attractable mathematically. Okay, and so we will talk about like this. So like when we study, for example, the central limit theorem, we talk first about the IID case, and then we will study a version of the central limit theorem in which the random variables are independent but not identically distributed. Okay, and so forth. Okay, so keep this in mind. And again, independence mean that the random variables, they observing one of them does not tell you anything about the other. Identically distributed does not mean that they are identical. It does not mean that they are equal, right? If two random variables, so if x is equal to y, if two random variables are equal to one another, then they are fully dependent, right? So if you know that there is a random variable x and then there is a random variable y, and that x is equal to y, so if you go and observe x, then you know what y is, because y is equal to x. Okay, so we are not saying that the random variables are identical. Okay, so identical, this is something, okay, or equal, but this is not what we are talking about here. It's identically distributed. They have the same distribution. The underlying distribution of each random variable is exactly the same. So if one of them is Gaussian, the other is Gaussian, as I said here in this example, and they have the exact same parameters. It's not, that one of them has a certain mean and the other has a different mean. Very important. So never do this mistake. Never treat identically distributed random variables as if they are identical. They are identically distributed. Typically, we will have identically distributed random variables that are independent. So independence means that they have, again, observing or measuring one of them will reveal nothing about the other. Okay, so very, very important. It's identically distributed, same distribution, and typically those will be also independent. Okay, they are not identical. Now, if we have two random vectors, so basically we have a bunch of random variables, x1 to xn, and we have another bunch of random variables, which is y1 to yk. Now, the two random vectors, so in total we have big N plus big K random variables. So if we say that the random vector x is independent of the random vector y, so we are saying that the joint CDF of those N plus K random variables can be written as basically the joint CDF of the x's multiplied by the joint CDF of the y's. Okay, so this is the joint CDF of the N plus K random variables. And if vector x and vector y, I say this, that these two random vectors are independent, I mean that basically you can write down the joint CDF of the x's and y's together as the product of two things. One of them will be the CDF of the x's, and the other will be the CDF of the y's. Note that when I say something like this, that two random vectors are independent, I do not necessarily say that the x's themselves are independent of one another. Okay, so what I mean is something like this. So the joint CDF of the x's and y's, if I say that random vector x is independent of random vector y, I can say that this function here, which is the probability that big x1 is smaller than small x1, big x2 is smaller than small x2, and so forth, it can be written as the joint CDF of the x's and the joint CDF of the y's. Can we write each one of those guys as a product? You can do this if also you have this further piece of information that the x's themselves are independent of one another and the y's are independent of one another. Okay, so but what I'm saying here, when I say that two random vectors are independent of one another, I'm saying that each random variable here is independent of a random variable there. Okay, but the x's themselves may be dependent and the y's themselves may be dependent. Okay. Now, if two random vectors are independent, okay, and so we'll take this for granted in this course, and this is very useful and very important. If we have the x's and the y's are independent, random vector x is independent of random vector y, then any function of the x's and any function of the y's will be independent. Okay, so this is very important, extremely useful. Okay, and again, we'll take it for granted. Now, you will see here that I am saying that the function should be Borel measurable. Okay, but for the purpose, I mean, this is like just for completeness and to make the writing a bit accurate. But for the purpose of this course, and typically in applications, whatever function you will encounter, things like taking a square root or exponentiation or logarithm or squaring, raising to the power n, and so on, all these things are basically Borel measurable. So you don't need actually to worry about this. The functions that you will use will be Borel measurable, and again, this is something that you can basically assume that it is valid and it is true. So for us, if you have x's, okay, and and y's, and the x's are independent of the y's, so random vector x composed of those random variables is independent of random vector y, which is independent of if random vector x, which is composed of those random variables, is independent of random vector y, which is composed of those random variables, then if you apply a function to the x's and apply another function to the y's, then basically the functions are independent. Each function itself will be a random variable, and these two random variables will be independent. So for example, if this is true, then x1 squared plus x2 squared plus xn squared is independent. So that's a function applied to those x's is independent of e to the y1 plus e to the y2 plus e to the yk, which is another function applied to the y's. So if you know that the x's are independent of the y's, then any function of the x's, so here let's say that this function is the sum of the squares, will be independent of any function of the y's, which here will be basically the exponentials. Okay? So very important again and very useful, because sometimes you start with this, this piece of information that those random variables are independent of those other random variables, but then actually in solving the problem you do not deal with the random variables, but you deal with the function of them. So basically, can you say that this function of those random variables is independent of this function of the other random variables? Yes, you can. And again, you do not need to go into details about checking Borel measurability or something like this. Okay, just go for it and use this idea. Very important and very useful. No, I didn't. I couldn't read the question. Can you please say it?
Can we argue the same that if, for example, we have the two random variable vectors x and y, and we apply the same function on both of them? So example G1 is the same as G2. It's still independent, right?
Yeah, they are still independent. I mean, so if you apply the same function, okay, that's a good question. So here I wrote G1 and G2 like for generality, but yes, okay, so let me write, so x1 squared plus x2 squared plus xn squared, that's another example, is independent of y1 squared plus y2 squared plus yk. Yes. So here, you know, the function which is like sum the squares, here again, I wrote G1 and G2, not necessarily to mean that like you should apply different function. No, you can apply the exact same function. Okay, you can apply the exact same function so long as the x's are independent of the y's. Then a function applied to the x's will be independent of a function applied to the y's, even if this function is the same thing. You know, like here, you know, in the second example, which like you sum the squares. Okay. Now, if we have a bunch of random variables inside the random vector, then then there are questions. I mean, each one of those random variables may be of a certain like type or something like this, and so on and so forth. And typically, we'll be like interested in cases. For example, this is the first case in which like every guy is a discrete random variable. Every guy is a discrete random variable, which means that every guy takes on finite or countably infinite values almost surely. Okay, so you may have like again random variables that everyone is discrete, and in that it may be useful, like rather than using the joint CDF. The joint CDF is there. It's well defined for any combination of random variables you can think of. But if you know that your random variables are discrete, you can just make things easier for yourself and use the joint PMF, so the joint probability mass function. And so the joint probability mass function will be the probability that big X1 is equal to small x1, big X2 is equal to small x2, up to big Xn is equal to small xn. Okay, so this is the definition of the joint PMF. Okay, and which is like an extension to the PMF of a discrete random variable. Now, what if you want to obtain the PMF of one of those random variables, given that you know the joint PMF? So what you do here, so remember, if you know the joint CDF, so you go to the other random variables and their parameters, you take the limit of those parameters going to plus infinity. Now, if you have a joint PMF and you are interested in the marginal, then what you do is that you sum over the other random variables. Okay, so suppose that you are interested in this thing, x1 is equal to x1, but what you have is something like this, x1 equal to x1. So this is the marginal PMF, which again is the PMF of one of the guys here, big x1, but you have the joint, so x2 is equal to x2 and x3 is equal to x3. So how can we use this one to obtain that one? So the idea is that you sum over the other random variables. Okay, so basically, if you take this joint PMF and then you sum it over all possible small x2 and you sum it over all possible small x3, so if you sum over all possible x2 and all possible x3, then after doing these summations, you basically obtain the PMF of x1. Okay, and so this is a way of getting the marginal PMF if you know the joint PMF. And this is not mysterious at all. This is the law of total probability, right? So if you think about the law of total probability, like suppose that you are interested in this thing, okay, and you cannot get it like sort of directly, then remember, what is the law of total probability? Is that, okay, let me write it like in the abstract form first, that if you are interested in event A, okay, then what you can do is that if your omega is partitioned into B1 union B2 union B3 and those guys are disjoint, then the probability of A is that you sum K, and then you have here the basically the probability of A intersection basically BK, right? This is the law of total probability. So it is exactly the same thing that we do here. So if you are interested in the probability that big X1 is equal to small x1, okay, then what you can do is that you can partition your space of possibilities by basically summing over all possible values of big X2 and big X3. So here the idea is that, you know, what are the possibilities of X2 and X3? So you take basically summation and X2 and summation X3, and you say, okay, this is the probability that X1 is equal to X1 and basically X2 is equal to X2 and X3 is equal to X3. So those basically are like the B events in the formula for the law of total probability. And so you sum basically over all possible values of X2 and all possible values of X3. And by doing so, you are left with the probability that X1 is equal to X1. And I emphasized last time that this comma that we use here is AND. So this comma here, again, won't harm if I repeat it. It's intersection, it is AND. Okay, so when we talk about random variables, you know, we typically use this comma, and again, it's nothing but, you know, it's an intersection or it is an AND. So if I write down something like this, it's the probability that big X1 is equal to small x1 and big X2 is equal to small x2 and big X3 is equal to small x3. So what we are doing is that, again, by summing over those guys, okay, and keeping X1 fixed at some value, you know, one of its possible values, then we obtain the probability that big X1 is equal to X1. So marginalization for, you know, discrete random variables with a joint PMF means that if you are interested in the PMF of one of the guys, you go and sum over the others, and you can extend this idea, right? So what if, again, if you take your set 1 to n and write it as, you know, basically two disjoint sets, IM J1 to Jn minus m, and you are interested in some of the guys, then you know, if you want to find the joint PMF and you know the joint PMF of basically every, you know, of all the collection of random variables, then what you do is that you sum over the others. Okay, so that's concrete example. So if you have 4 random variables, x1, x2, x3, and x4, and now what you are interested in, for some reason, in some application, is that you want the joint PMF of the second and fourth guys, okay, then, and you know the joint PMF of the 4 guys, then what you do is that you sum over the first and you sum over the third. So you sum over the possible values of x1 and the possible values of x3. And you do this sum, you end up with the joint PMF of x2 and x4. Okay, so here you need to do this, basically this summation. Now, the expectation of a function of those random variables is, so again, you may, you know, this is not new, this is Lotus, this is the law of the unconscious statistician. So if you want the expectation of this function of the random variables x1, x2 till xn, then what you do is that you sum all x's, you take the possible values of the function, and you weight each possible value by its respective probability. Remember that the PMF is nothing but this probability that x1, big x1 is equal to small x1, x2 is equal to small x2, and so forth. So expectation of a function of those random variables, again, is you take the possible values of the function, and you take each possible value of the function and multiply it by its respective probability, and then you sum, and this will give you the basically the first moment of function g of x1 till xn, or expectation. Now, independent, if your random variables are discrete, are jointly discrete, and if they are characterized by a joint PMF, then independence here means basically that the joint PMF can be written as a product. Okay, so the same idea as the CDF. So independence here means that I can write down the joint PMF. Okay, so if you have 2 random variables, so probability x1 equal x1, x2 equal x2. So if we have independence, so if we have independence, then you can write down this joint probability, which is like x1 and x2 together and with an and, then this is probability that x1 is equal to small x1, probability x2 is equal to x2, and this is for every x1 and x2. Okay. So independence again means that you can take the distribution. Okay, so we started with the CDF on the previous slide, and we can write the CDF as the product of the CDF of each one. If you have a joint PMF, then same thing. Then basically independence means that you can take the joint PMF and you can write it as the product of the PMF of each one of those guys. Okay, and this is the meaning of independence. The interpretation. What does it mean that two random variables are independent? Again, what works very well in applications is that two random variables are independent if the value of one of them. So you have x1 and x2, and someone told you, x1 in this particular experiment is equal to 5. Okay, maybe you are measuring the length of something, and this is like 5 centimeters. Then if x1 and x2 are independent, then knowing that x1 is equal to 5 centimeters, tell thing about x2. Okay, if you want to gain information about x2, then you can try to measure it directly or something like this. But no information about x2 from x1, so this will be independent. As a mathematical formulation, it means that you can take the PMF and write it as basically a product. And this thing is not, again, it's not like mysterious or anything. Remember how we define the elements of events. So basically we say that event A and B are independent if the probability of A intersection B is the product, right? So again, it's like, these things that we are writing down are inherited from the basic, the basic properties of a probability measure. Now, if we have two random vectors, x and y, and two random vectors are independent of one another, it means that I can take the, the joint PMF of both guys, which is the joint PMF of those big N plus big K random variables, or in our case here, discrete random variables, and we can write it as a product. So we can basically isolate these two PMFs, and multiplying them will give us the joint. And now the expectation of a product. So if the x's are independent, basically this line here is again under the assumption of independence. If you have a function, of the first collection of random variables, the x's, and you have another function of the y's, and you know that the x's and y's are independent, then it means that the expectation of G1 multiplied by G2 will be the product of expectation. So this is very important. So if x, which is equal to x1 to xn, is independent of y, which is y1 to yk, then it means that then, again, very important and very useful, any function applied to x's is independent of basically any function applied to the y's. And these two, as I said, in response to the question, basically these two functions may be the same thing. Maybe you will just, maybe the function is that you sum the x's and you sum the y's. Okay, so it's not a problem. Maybe big N is equal to big K. Okay, so it can be a different function, it can be the same function, but in any case, these two guys will be independent of one another. And if they are independent of one another, also if you have an expectation of x1 till xn, this expectation of the product can be written as a product of expectation. Continuous random variables, yes, I mean, this will be in the next slide, exactly. This will be the next, right? So this will be expectation of the first guy and multiply the expectation of the second guy. Okay. So yeah, the second sort of interesting case is what if your random variables are basically everyone is absolutely continuous, and we have a random vector. We say again the rigorous definition is that the random vector composed of the variables x1, x2 till xn is said to be absolutely continuous if the probability of any Borel set in Rn of measure 0, of Lebesgue measure 0, is 0. Okay, so that's like the rigorous definition. So if this is true, if for any Borel set in Rn that has domain measure 0, that if basically the probability of this parallel set is exactly equal to 0, then we say that our random variables are jointly absolutely continuous. Again, what useful for us in practice is, this idea that jointly continuous random variables, they are characterized by a joint PDF. Okay, so the jointly discrete random variables are characterized by a joint PMF. The jointly continuous random variables are characterized by a joint PDF. Okay, so this will be something like this. A joint PDF will be a function, right, as x1, x2 till xn, x1, xn. And what is this joint PDF? Okay, what basically are the properties of this joint PDF? It's like a PDF, so it's non-negative. It should be a non-negative function. It cannot be negative at some value or something. It cannot be negative on, strictly speaking, it cannot be negative on any subset of Rn that is of Lebesgue measure that is strictly positive. So it should be non-negative. But it's not a probability. So like a PDF, the joint PDF is not a probability. So there is no problem if this joint PDF exceeds 1. There is no problem if this joint PDF is an unbounded function. These are not a problem. So what is needed is that basically the function is non-negative almost everywhere in Rn. And you can obtain the CDF from this function via integration. So again, it's a generalization of the one random variable case. So if you want to find the joint CDF, which is the probability that x1 is less than or equal to small x1 up to xn less than or equal to small xn. So how can you obtain this joint CDF? If you know the joint PDF, you simply integrate. So integrate from minus infinity to x1, minus infinity to x2, and so forth. Okay. So by integrating the joint PDF, you can get probabilities. You can get something, for example, like the CDF, if you start your integrals from minus infinity to basically to small x1, small x2, and so on. And the joint PDF can be obtained from the joint CDF via differentiation, but here in the case of multiple random variables, we have partial differentiation. So basically, the joint PDF is the nth partial derivative of the joint CDF, in which you partially differentiate with respect to each one of those guys once. Okay, so and this formula will be true wherever basically the partial derivatives exist. Okay. Now, if you are interested in this probability, for example, if you have two random variables and you're interested in something like this, a1 to b1, comma a2 x2. So if you want x1 to be between a1 and b1, and you want the probability that x2 is between a2 and b2. So how can we obtain this probability from the PDF? You just integrate over the respective region. So you take the joint PDF. So the joint PDF will be represented by this small f. So here the notation in the course, and it's sort of the standard notation. Basically, for the joint CDF, use big F, but for the joint PDF, use small f. So you take the joint PDF, okay, and you integrate it. So again, the joint PDF itself is a probability density. It's not a probability, but you can convert it into a probability by integration over parallel sets. And so you can basically, if you are interested in the probability of this event here, you can integrate x1 from a1 to b1, and you can integrate x2 from a2 to b2. Okay, so this will be the probability. If you want from the PDF to get the CDF, you basically do the integrals from minus infinity, because the CDF, it's interpreted as the probability that x is, less than or equal to some, threshold value. Okay. Marginalization is like for the discrete case, but now you integrate rather than sum. So suppose that you are interested in the marginal PDF of one of the guys. Then what you do is that, and again, it's the law of total probability. It is nothing else. It is the law of total probability. You want to find the joint, you want to use the joint PDF to obtain the marginal PDF of xk. Then what you do is that you integrate over the others. Okay, so again, let's give a concrete example. So if you have x1, x2, x3, x4. Suppose that you are interested in the joint PDF of x1 and x4. Okay, then, so the joint PDF of x1 and x4, okay, is, again, you take the big one, okay, 3x4, which will be parameterized, x1, x2, x3, x4. You are interested in x1 and x4, so you integrate with respect to the other ones, x2 and x3, and you do so from minus infinity to infinity, minus infinity to infinity. If your random variables are non-negative, then you integrate from 0 to infinity and so forth. Okay, but generally you will integrate from minus infinity to infinity. Okay, so this is how you obtain, if you want basically just the PDF of x1, then you integrate with respect to x2, x3, and x4. Okay, so again, same idea, but for the PMF we do summation. For the PDF we do an integration, so that we can basically extract the marginal PDF, the PDF of one or a subset of the guys from basically the joint PDF of all of them. Lopus is also here. If you want the expectation of first moment of a function of those random variables, then you take the function, you multiply it by the joint PDF, and then you integrate, and this is how you get the expectation. Here I am sort of assuming that the expectation is, exists and is finite. Okay, so this is again implicit here, that if the expectation exists and is finite. And here is what I said about using the PDF to obtain the probability on intervals. So basically you just integrate. In PDF you convert it into probability by doing integrals. This is like sort of like the easy situation, but when we solve problems, as we will see, typically we are interested like in more complicated regions. So like basically this region is like, if you have like x1, x2, typically we are not just interested in like the probability that x1 and x2 are inside one of those rectangles. So typically we are interested in regions that may look something like this, for example, maybe what is the probability that x1 and x2 are in this region? Let's say this trapezoid here, and so on. Okay, so so typically those integrals will not be as easy as they look. Basically you need just to be careful in writing down the limits of integration, and we will do like exercises to show exactly how to do this. The random variables are independent if joint PDF can be written as a product. If random variable x, if random vector x is independent of random vector y, okay, it means that every x is independent of every y. Not maybe the x's among themselves they are dependent, maybe the same applies to the y's, but every x is independent of any y. And if you want to write the joint PDF of the x's and the y's together, you can write it as a product of the PDF of the x's written alone and the PDF of the y's written alone, and those guys are multiplied together. If you have independence, then when you take the expectation of a function of the the x's and another function of the y's, if the x's and y's are independent, then what you can do is that you can say that the expectation of the product is product of expectations. Okay, so you can write this in words that so in the case of independence, the expectation of a product is a product of expectations. Okay, it makes life much easier than the dependent case. Okay, In case there is dependence, we will learn some tricks later in the course how to deal with this. So we'll learn about something called iterated expectations. Some people call it the tower principle, which will allow us basically to sort of efficiently compute expectations if we have like dependence. In some cases, of course, some cases of dependence are very difficult to handle. Okay. If you have two random variables, x and y, then you can define something called the covariance. And the covariance of x and y is defined as this function here. So covariance xy is basically expectation of x minus expected x, y minus expected y. Okay. And so you take x, you subtract from x its first moment. So again, the assumption is the implicit assumption. If I subtract the first moment, then automatically I mean that it is it exists and it is finite. So you subtract the first moment from x, you subtract the first moment from y, then you multiply x minus expected x, y minus expected y, take the expectation of this thing. And so this is something called the covariance. Okay. And the covariance can be equal to 0, and it can be positive, and it can be negative. And the case of 0, if the covariance is equal to 0, then we have a term that is used a lot in probability and statistics, which is that we say that the random variables are uncorrelated. Okay, so if covariance xy is equal to 0, we say that x and y are uncorrelated. They are uncorrelated. Okay, so automatically, if I give you a problem and say that x and y are uncorrelated, automatically you mean that you understand this to mean that the covariance of x and y, if you compute it, you will get exactly 0. Okay. And maybe in the next slide or something, or later in this lecture, we will basically, see the relationship between independence and uncorrelatedness. Okay, so I mean, I'm getting ahead of myself, but if two random variables are independent, then they are guaranteed to be uncorrelated. The converse is not necessarily true. Okay, so independence implies uncorrelatedness. So if I give you an x and y, they are independent, and then if you go and compute their covariance, you are guaranteed to get a 0, meaning that x and y are, they are not just independent, they are also uncorrelated. But if I give you two random variables x and y and their covariance is 0, meaning that they are uncorrelated, perhaps they are dependent. Okay, so that again, independence implies uncorrelatedness. The converse is not necessarily true. Covariance is sort of a measure. Again, how to assign a meaning to these things. One way of understanding covariance, when basically if you have positive covariance. Okay, so if you have positive covariance, you are saying that if x, there is a tendency that if x is above its mean, that y will also be above its mean, and if x is below its mean, then y will be below its mean. Okay, which means that positive covariance means that x minus expected x and y minus expected y, they tend to have the same sign. Again, let me repeat. So a positive covariance means that there is a tendency, it's more likely that if x is above its mean, then also y is above its mean, and if x is below its mean, then y is below its mean, which means that x minus expected x and y minus expected y, basically they have the same sign. Okay, so they are both positive or they are both negative. It's not guaranteed, it's a statistical statement. Okay, so they tend to be of the same sign. Now, negative covariance will be understood basically that x minus expected x and y minus expected y, the opposite sign. Okay, so if x is above its mean, then then it's likely that actually y is below its mean. So this is the meaning that if you have negative covariance. Okay, so this is the meaning of covariance being positive or negative, and and basically between these two guys there will be the value of zero covariance, which is this uncorrelatedness business. Okay, then there are properties for covariance, and again they follow from the definition. So for example, covariance x and y is covariance y and x. Okay, because like it's expectation, it's an expectation of a product, right? And so you can basically say that this thing is expectation of y, expected y, x minus expected x, and so basically it won't make a matter a difference whether you consider x first or y first. However, so this is very important. Let's write it in red. Not true for complex valued random variables. What is complex valued random variables? We have never talked about them. Yes, that's true. Most likely we'll start talking about them after the second exam. So in practice, it is sometimes nice if we take two random variables and combine them as a complex quantity, which we call a complex random variable. Okay, and so for complex random variables, when we define the covariance, one of those brackets will have a conjugate. Will have a complex conjugate, okay? And so basically this will not generally be true. So covariance xy, so this is for the random variables that as you know of, but once we extend our topics to include complex valued random variables, then this will not be true again, because there will be like a conjugate or something like this, okay? Now covariance xx is variance x, right? Because if you replace y by x, what do you get? You get the expectation of x minus the mean value of x squared, okay? So, which is by definition the variance of x, okay? So covariance xx is the variance of x. Now you can show that basically covariance x, y plus z is covariance x and y, covariance x, commas. Again, these are not difficult to show, that just apply the rules. So what is this covariance? And so x, okay, this x will be, again, you take the first random value, don't forget to subtract the mean. Very important. The definition of covariance requires that you need to subtract the mean. If the mean is zero, then it's fine. If the mean can be zero. But if it's not zero, then you need to subtract the mean, okay? Very important. It's inherent in the definition of covariance. And so you have this guy. And then the second guy, you will basically take y plus z and then minus the expected value. So y plus z minus the expected value of y and z. Y and z. Okay, so this is by definition the covariance of x on the one hand and y plus z on the other hand. Well, we know that expectation is a linear operator, right? So expected y, expected z is, so this is minus expected y minus expected z, because expectation is linear. And then you can write this as expectation, x minus expected x, write this, and then you can take the y, together with minus expected y, okay, and then you can take the z minus expected z, and then you can multiply and apply again the linearity of expectation, so you will get expectation of this times this, so this will be the covariance of x comma y, and plus, again, because the expectation is linear, expectation x minus expected x minus multiplied by this guy, and so this will give you covariance x comma z. So again, these things are, I skipped the derivations here because they are sort of like they follow directly from how the covariance is defined. Okay, covariance ax plus b, cy plus d, and again you can, like, as an exercise, do this yourself, will be, so covariance of a linear transformation applied to x. So it's a constant multiplied by x, and then you add another constant, and then if you take y and multiply by a constant and add another constant, so what do you get for the covariance? What you get is covariance xy, and then it is multiplied by the product of these two guys, a and c. What about b and d? Disappear. They will disappear. Okay, so basically you can add here anything, and this will not impact the covariance. And the idea is simple. It's not a mystery or anything. It's because if you compute the expected value of this guy, it will include the constant p. So if you take the random variable and subtract its first moment, this constant will disappear. So I mean, so by definition, because covariance requires that you subtract the first moment from the random variable, then those constants will be like sort of irrelevant. But those are relevant. Okay, so covariance ax plus b, cy plus d will be, you should have basically this product of those two vectors, and then covariance xy, while b and d are, you can be anything, and you will get the exact same result. Also, you can rewrite the covariance as the expectation of the product minus basically the product of expectations. Okay, so sometimes actually this formula is like is a bit more convenient to use. Derivation, again, very straightforward. So we start with the covariance of expectation, x minus expected x, y minus expected y. Okay, and so multiply the two brackets. So if you multiply the two brackets, you will get basically four terms. What are these guys? X, y. Okay, and then minus x expected y, minus y expected x. Okay, and then you have the product of these two expectations plus expected x, expected y. Okay, and then expectation is a linear operator. So basically the expectation of these four terms is the expectation of each one of the guys, and then you put the respective plus or minus sign. So this is expectation xy minus. So what is this thing? This is a constant. This is a constant, right? It's the first moment of random variable, right? It's some finite number. Okay, and so expectation x multiplied by this constant, because of the linearity of expectation, this constant will just will just appear outside, and then you are taking expectation of x. So this will be expectation x, expectation y. Expectation y is a constant. Here it's basically the same story. It's expectation x as a constant, which you can pull outside, and then you can take the expectation of y. Okay, and then this is a constant, this is a constant, and the expectation of a constant is a constant. It's the same constant itself. So this will be expectation x, expectation y. Okay, so this basically, so we have minus the product plus the product ones. So this is equal to the expectation of the product minus expectation x, expectation y. Okay, so the covariance, you can compute it by taking, you subtract expected x from x, you subtract expected y from y, you multiply and take expectation. So this is like the definition. But also you can do something like this: expected xy, and then you can multiply expected x times expected y and subtract, and this will give you the also the covariance. Okay. Now we define something called the correlation coefficient, which is sort of a normalized covariance. Okay, so basically the correlation coefficient of two random variables x and y is that we take the covariance. Okay, so we compute the covariance, and after computing the covariance, what we do is that we divide by the standard deviation of x and the standard deviation of y. The standard deviation is nothing but the square root of the variance. Okay, so we take covariance x comma y, and we divide by the square root of variance x, and we divide by the square root of variance y. Again, those are called the standard deviation of x and the standard deviation of y, and this thing will give you something called the correlation coefficient. Okay, note something, that this expectation of xy without subtracting the first one, this is called the correlation between x and y, Okay, so if I tell you compute the correlation between x and y, I mean expectation of x times y without subtracting the first moments. Okay, covariance, you need to subtract the one. Correlation coefficient, it's obtained by taking the covariance, must be the covariance, and basically dividing it by the square root of variance x, square root of variance y. Now, by doing this division, what you do is that you get a quantity that is sort of normalized. In other words, you can show that basically the correlation coefficient, of course, if the two random variables are uncorrelated, then if they are uncorrelated, then their covariance is equal to 0, and the correlation coefficient will be 0. If the covariance is positive, the correlation coefficient will be positive. If it's negative, if the covariance is negative, the correlation coefficient will be negative. But basically, it is guaranteed that the magnitude or the absolute value of the correlation coefficient is less than or equal to 1. So its maximum possible value is 1, and it's on the other side it cannot go below -1. Okay, so the magnitude of the correlation coefficient is between 1 and -1. And you will take the proof of this. So the proof is using an inequality called the proof using the Cauchy-Schwarz inequality, which you will study in the next tutorial session, the Cauchy-Schwarz inequality. Okay, and the Cauchy-Schwarz inequality, so if you have A and B, okay.
Professor, I just want to ask, what does the correlation coefficient tells us? Like, you said that, for example, the covariance tells us the tendency.
It is the same. It is the same information. It is a measure of correlation. It is again the same story of covariance. You know that basically, if it is positive, then basically x and y, or specifically x minus expected x and y minus expected y, they tend to have the same sign. So if we know that x is above its average, then it's likely, you know, that y will be also above its average, and if x is below the average, y will be below the average. The correlation coefficient is just the meaning of covariance, so the meaning will not change, but it has the nice property that its values are bounded. So basically, by dividing by the square root of variance x and variance y, basically we have a quantity now that is basically it cannot go above 1 or below -1. But the meaning is like, you know, it's that covariance. It's just normalized covariance to get this, you know, to get this nice property here.
Okay, thank you.
Okay, and basically for the Cauchy-Schwarz inequality, if you have two random variables, A and B are two random variables, okay, and an expectation of AB, the absolute value is less than or equal to basically the square root of expectation of A squared, expectation of B squared. Okay, so this is the Cauchy-Schwarz inequality for random variables, and what we can do here is apply with A equal expectation x minus expected x and y minus expected, right? Sorry, B y minus expected y. So if you apply basically the Cauchy-Schwarz inequality, by the way, those inequalities, you know, I told the TA that basically you are not like responsible for the proofs. Basically, there are the proofs, so I will provide you with the proofs of those inequalities. You know, so you will study the Cauchy-Schwarz inequality, Holder inequality, Lippanov inequality, and the Minkowski inequality. But you know, you can just learn how to use these inequalities. For us, this will be the most important thing, how to employ them to, you know, achieve some result. But the proofs are also there, but they are not like required. Okay, so they are optional. Okay, so what we can do is that we can apply this expectation of, you know, x minus expected x. So this is my first random variable. My second random variable is this one here. Okay, and according to the Cauchy-Schwarz inequality, this is less than or equal to the expectation of the square of the first guy and the square of the second guy. Okay, and let's see what we have here. What is this thing? What is this? By definition, this is covariance. So the absolute value of covariance xy is less than or equal to, what is this thing? X minus expected x squared, and then you take expectation, that's the variance. Okay, so this is square root variance x. The first term is variance x, and the second one is variance y. That's it. Okay, so basically, so it's like this is like the idea behind the correlation coefficient, that using using the Cauchy-Schwarz inequality, you can show that the magnitude of the covariance is less than or equal to the square root of variance x variance y, and hence if you take the covariance and you scale it, you know, by dividing it by the square root of variance x square root variance y, what you get is something that is always less than or equal to 1. So it's sort of like, you know, bounded. You know, you put like a maximum. You deal with something that is like nice. It's between -1 and 1. That's it. Okay. So again, the motivation behind the correlation coefficient is to normalize and to get something that that basically is living on just, you know, this nice interval between -1 and 1. And it follows directly from applying the Cauchy-Schwarz inequality. And in the tutorial session, you will basically learn how to use it in other situations. So I said that basically if the two random variables are independent, then they are uncorrelated, okay? And uncorrelated means that the covariance of x and y is equal to 0, so this is uncorrelated. And automatically, if the covariance of x and y is equal to 0, then the correlation coefficient is also equal to 0, because the correlation coefficient is nothing but the covariance, and then you divide by the square root of x, of the variance of x and the square root of variance, okay? But can you have two random variables that are uncorrelated, and yet they are dependent, okay? So uncorrelated, it's just a weak concept. So if two random variables are uncorrelated, can you think of them that knowing something about one of them will tell you nothing about the other? No. Generally speaking, no. This is not true. To say such a strong statement, that basically no information about x by observing y, then you need the concept of independence. Uncorrelated is a very mild form of a weak relation between x and, so you can say that x and y are weakly related, but you cannot say that basically if you know x, then you say nothing about y. Two random variables may indeed be uncorrelated, and yet they are dependent. Okay, so how to show that the converse is not true? One way of showing it is just to provide one counter example. So here is our counter example. So we have two random variables, x and y. Let's take both to be discrete. And this is the joint BMF of the guys. So this is 1, 0, and this is the point. So this is the point 0, 1, and this is the point -1, 0, and this is the point 0, -1. So x comma y basically are one of four ordered pairs in the two-dimensional plane, and xy basically you can be in any of xy can take any one of those four values with equal probability. So the probability of each one of the guys is 1/4. Okay, so what is you can compute, for example, what is basically what is the marginal. So this is a nice exercise to apply. What is the probability that x is equal to 0? Here, I mean, because the number of possible values for x and y are basically very limited, they can take only one of four possible values, then you can easily get things without you can do things without doing a summation or something like this. What is the probability that x is equal to 0? What is the probability that x is equal to 0? So probability that x is equal to 0 is basically, let me write it explicitly. Here it's written directly, but this is x equals 0 is the probability that x is equal to 0 and y is equal to 1, plus x is equal to 0 and y is equal to -1, right? This is basically, I mean, if x is equal to 0, then it can be 0 and y is 1. It can be 0 and y is -1. Nothing else. Nothing else. Okay, and so this is 1/4, and this is 1/4, and so this is 1/2. Okay, so this would be the probability that is 1/2, like this. What is the probability that x is equal to 1? Well, x is equal to 1 only for this point, and so this is 1/4, and x equal to -1, this is only 1/4. It will be this other point. What is the first moment of x? Then now we know that x itself, it has the possible values are -1, 0, and 1. This happens with probability 1/4, this 1/2, and this is 1/4. What is the first moment? You take each possible value and you weight it by the respective probability. So 0 times 1/2, 1 times 1/4, -1 times 1/4, and then you add, so the expected value of x will be 0. You can do the same for y. So you find that y, basically, y also, it is 0 with probability 1/2, 1 with probability 1/4, -1 with probability 1/4, and its first moment is exactly equal to 0. X and y actually are identically distributed. Here they are. So this is an example in which the two guys are identically distributed. Now suppose that you want to compute the covariance. So the covariance is basically covariance xy. The formula that it's xy, right? In our case here, because expected x is 0, expected y is 0. So basically the covariance is equal to the correlation expected x and y. So what is expected xy? So we learned this. Again, this should not be interpreted as something that is very complicated or anything. Remember that if you have if you have a function of x1, x2, xn, like this, and you are interested in the expected value of a function of those guys, what do? Lotus, which is basically the law of the unconscious statistician, which is you just sum over all possible values, okay, of the function, weighting each value by its respective probability. x1 is equal to x1, and so forth. Okay, so if I give you here, what is expected xy? What is expected? So expected xy. So what are the possibilities for xy? Okay, xy is a function of x and y. It's basically that you multiply them. So this will be 0 and 1. Okay, so 0 and 1, which is this point, multiply its probability, which is 1 over 4, plus 1, 0, multiplied by its probability, which is 1/4, plus 0 minus 1, multiplied by the probability, which is 1/4, plus x here is minus 1, and y here is 0. So the function is that you take x and y, multiply them together, and the probability is 1/4. You will find that each one of those terms, it has a 0, and so this thing will be 0. So expected xy is 0, and expected x is 0, expected y is 0, and so actually the covariance here is 0. So according to the definition, you say that x and y are uncorrelated. It's true. X and y are uncorrelated here. Okay? But are they independent? Okay, are they independent? So now suppose that basically what is the probability of x equal 1 and y equal 0? So this probability is 1/4. This probability is 1/4. Again, it's a given that x and y can take any one of those 4 values with the probability 1/4. So what is the probability that x is equal to 1? So we computed this, it was 1 over 4, and the probability that y is equal to 0, we computed this was 1/2. And what is the product? The product is 1/8, right? So remember that to be independent, it must be the case. So independence requires that probability that big X is equal to small x, big Y is equal to small y, is equal to the probability, to the product of the probabilities for every x and y. This is independence. So if you can come up with one counter example, in which like this probability is not equal to the product, then x and y are not independent. So they are uncorrelated because the covariance is equal to 0, but they are not independent. They are dependent. Now, actually, can we use the intuitive meaning of independence like to know that x and y are dependent? Of course, this will not like be a proof that they are independent. To show that they are dependent, you will need like to do something like this: provide a counter example, show that the probability, a joint probability is not the product. Okay, but intuitively, why actually x and y are dependent? So dependence, again, like in practical applications, we think of two random variables are dependent. That if you know something about one of them, then you gain information about the other. Then you know some information about the other, right? So if I tell you that x is 1, automatically y will be 0. Automatically y will be 0, because if x is 1, there is nothing possible except that y will be equal to 0, right? So this shows that you can know something about by observing x. Okay, again, if I tell you that, if I tell you that x is positive, so something x is positive, and we have x and y basically with this distribution, then no way y is positive, then y is 0. That's it. Okay, so this is this cannot happen if we have independence. Independence means really that if you know one of the random variables, you can say nothing about the other. Okay, so basically the two random variables intuitively, you can basically think of knowing something about x and inferring something about y, or vice versa. They are dependent, and showing it formally means that you show that the condition of independence is violated. Okay, by showing something like this, but they are uncorrelated. Okay, so if you know that two random variables are uncorrelated, well, it's not, you cannot make inside, you cannot like start thinking about them, that one random variable is telling us nothing about the other. This will not be correct. Uncorrelatedness is, it's just that the covariance is equal to 0. They are, it's a weak form, a very, very weak form of independence, and it should be avoided, like to think that basically the random variables do not basically tell you something about each other. Now, if you have random vectors, so when I talked about covariance, I talked about basically two random variables. But we can extend the concept of covariance to random vectors by computing the covariance between each two components of a random vector, right? So if you have a random vector, let's say that you have a random vector which is basically x1, x2, and x3, right? And so you can think of basically x1 with x2, x1 with x3, and x2 with x3. And so we can compute. Again, covariance, by definition, it's defined to be something that can be computed for two random variables. You subtract the mean of the first from the first. You subtract the mean of the second from the second. You multiply, and then you take expectation. So for random vectors, what we can do is that we have this concept of a covariance matrix. And the covariance matrix here for those guys is a matrix that looks like this. So if we have three random variables, we put covariance x1, x1, covariance x1, x2, covariance x1, x3. Then we have covariance x2, x1, covariance x2, x2, covariance x2, x3. And then we have covariance x3, x1, covariance x3, x2, covariance x3, x3, right? So what you do is basically that, for a random vector, you compute the covariance by taking one, each row here will be like the first row, you take x1 and you compute its covariance with every other guy and actually with x1 itself. Now we understand, that basically covariance of something with itself, this is basically the variance of x1, and this will be the variance of x2, but I mean, you can say that it is covariance x1, x1, x2, and this will be variance x3. Okay, so you generate each row here again by computing the covariance of one of the random variables with all the components of the random vector, including with itself, okay, variable with itself. And by doing this, we construct a matrix, and this matrix will be called the covariance matrix. Okay, so this is the special case when we have just three random variables, but this case can be generalized, and for basically an n by n covariance matrix, yes, this matrix is for for real, for random variables as we know them till now, this matrix is symmetric. Good observation. So yes, this matrix is symmetric. Symmetry here comes from the property of covariance that I talked about earlier, which is that covariance x, y is covariance y, x. Okay, so because of this property that we have here, then yes, this is a symmetric matrix. Okay, this symmetric matrix can be written in a nice form. It can be written as the expectation of the outer product of two vectors, right? So let me go to the three vectors, three random variable case. So we write a vector like this. Okay, x2 minus expected x2, and then x3 minus expected x3. So take each one of the random variables and subtract its mean. Now take this vector, which is a column vector, and multiply it by basically the row version, which is basically this vector here. So this is x2 minus x2, x3 minus x3. So this vector is 3 by 1, and it's column vector. And this vector is a row vector, which is 1 by 3. And this vector is just the transpose, the column vector. So if you take a vector like this multiplied by a vector like that, we say that this is the outer product. And basically, if you do the multiplication, you will find what? So if you do the multiplication, you will find that you will get x1 minus expected x1 squared, and then you get x1 minus expected x1 multiplied by x2 minus x2, and so on. And when you to apply expectation, applying the expectation to a matrix just means that you apply to each element, and when you apply to this element, you get the variance of x1. When you apply to this element, you get the covariance of x1 and x2, and so on and so forth. Okay, so sometimes it's very useful, like, to think of the covariance matrix as the expectation of the outer product of vector x minus expected x by itself.